So, if we do that process at all different latitudes, and we map the derived water influxes that we get from each latitude along magnetic field lines back to Saturn's ring plane, then this is what we see here in this plot. So the bottom axis is Saturn's equatorial radius in terms of Saturn radii. So the Saturn rings, the main ring system, the ABC rings, are from about 1.25 Saturn radii to 2.25 Saturn radii. And then the green curves show the derived water influxes from the model comparisons with the observations based on latitude at the top or mapped to Saturn's equatorial ring plane and Saturn radii at the bottom. Okay? The main point from this figure is that we see a stronger influx of water at the inner edge of the B ring at about 1.5 or 1.6 Saturn radii. So now you might also think to yourself, why do we see a stronger influx there when interior to that, so about say 1.3 Saturn radii in the C ring, I've already told you that gravity would win and it would pull in all of the ring particles that are generated in the C ring. Well, the easy answer is that you can see in gray here, this is a plot of the ring optical depth versus radius, which is essentially a proxy for density. So the C ring has a very low optical depth, meaning a very low density. In other words, the C ring has already been shaped by this erosion process. So it was likely more dense before, and then all over time, over thousands of years, millions of years, perhaps billions of years, the rings have been eroded, and these particles have been sucked into Saturn's atmosphere. Okay? So that's the most likely explanation there. So, using those derived water influxes, we can then estimate what that means about the rate of mass loss from Saturn's rings. And if we know about the rate of mass loss, then we can compare that with the mass of the rings and get an estimate for the lifetimes of the rings. So, here I've outlined in a table the total mass in the A ring, the B ring, and the C ring, and then the derived ring mass loss rates in terms of grams per second. Based on those masses and those mass loss rates, you can derive a maximum lifetime from this erosion process, this ring-ring process. And you find in billions of years that the limit of the lifetime of Saturn's rings is rather large. So this erosion process is not likely to erode the rings over a time scale that is shorter than the lifetime of our solar system, for example. However, I should also point out that these are just upper limits because we don't know exactly what the particle is that's coming from the rings into the atmosphere. So these estimates are assuming that that particle is an ion, say H2+, H2O+, whereas it may in fact be a much more dense grain or dust particle. Okay? So it's also worth pointing out that we don't have a good idea of how old the rings are right now. So some current estimates in the literature for the lifetime of Saturn's rings range from around 4 million years to 4 billion years. In other words, they could be relatively young, or they could have existed for the entire lifetime of our solar system. So by following up with further ring-ring observations, we can help to refine this estimate and therefore help to refine, possibly, the lifetime of Saturn's rings. Okay, so now I'm going to transition into some observations from the Cassini spacecraft, which has been orbiting Saturn, or was orbiting Saturn from 2004 to 2017. And so in this animation you see here, this shows Cassini's 23 final orbits. Starting from about November 2016 to September 2017, Cassini executed a series of orbits, first just outside the main ring system, just outside the F ring. So Cassini, at closest approach during its elliptical orbit, was just outside the ring system in the ring plane. And then it also executed 20-some so-called proximal orbits. And these orbits are what's illustrated here. These orbits Cassini transitioned through the upper atmosphere between Saturn's interior to Saturn's D ring. Okay? And the overall portion of this mission of the Cassini spacecraft is called Cassini's grand finale. So here are the Cassini proximal orbits represented in a slightly different way. So here on the y-axis, I'm showing distance of Cassini at closest approach in kilometers. And then on the y-axis is essentially time. So each of these x's marks the point of Cassini's ring plane crossing. And then the pluses and the other symbols represent different aspects of each orbit. Okay? So we're seeing 23 orbits. And they're separated into 3 broad categories. So on the far right of the diagram are the so-called in situ orbits. These ones are actually in the region of the atmosphere, directly sampling the ionosphere where H3 plus is. Okay? Then there's some middle altitude orbits where they're still sampling the atmosphere, but they're above most of the H3 plus that we've been talking about. And finally, there are some high altitude orbits where they're essentially, Cassini has been essentially sampling the D ring on each pass. Okay. Now, notice we're showing here distance from the Saturn center in kilometers. And recall that Saturn radius is essentially 60,000 kilometers, although that radius varies with latitude because Saturn is an oblate spheroid due to its rapid rotation. Okay? Now, just to summarize ring rains, it's raining on the atmosphere of Saturn, and the rings are the cause. And this rain has a lot of interesting aspects to it that might reveal physical processes of the Saturn system. So the signatures that tell us that this ring is happening primarily come from looking at the H3 plus ion in Saturn's upper atmosphere. This measurement was the first time that ion densities in giant planet ionospheres at low latitudes were measured. And it's the first ground-based constraint on upper atmospheric temperatures. And finally, looking at the signature of H2+ gives a lot of insight into the ring-atmosphere coupling processes and into the mass loss of Saturn's rings, and therefore the ultimate lifetime of Saturn's rings. So in the future, what we need to do is to follow up on this ring. This is an initial measurement of Saturn's ring, but there's a lot more work that could be done. So from the ground, we can do follow-up observations with large telescopes, so Keck, IRTF, or Very Large Telescope, VLT. These observations can continue to monitor the variation of H3+ in terms of latitude and time. So we might expect there to be some spatial and temporal variability in the rate of ring mass loss or ring rain. And in addition, they can give us better constraints that we can use with models to further improve our constraints on the ring mass loss rates. From space, there's more to do, but most of it has to do with continued analysis of Cassini's grand finale data set. So Cassini mission ended in September 2017 when essentially, since they ran out of fuel, they decided what's the best way to end the mission. And the best way was to execute these series of high-risk orbits that would get really near the ring system and get unprecedented data of Saturn's rings, and they would directly sample the upper atmosphere, again, unprecedented data of the upper atmosphere, and give you a whole rich, new, exciting data set to work from, and then ultimately just crash into the planet. And the reason they want to crash into the planet, this happens quite often with NASA spacecraft, is because what they don't want to do is to risk messing up our search for habitability or life elsewhere in the solar system. So if you remember, I mentioned the moon Enceladus. Saturn's moon Enceladus has these water vapor plumes that fill Saturn's space environment and generate the E-ring at Saturn. These water vapor plumes are strong circumstantial evidence for subsurface liquid water oceans. And liquid water, we think, is one of the main ingredients for life as we know it. So therefore, Enceladus is a great candidate for searching for life in the solar system. And rather than take some small risk that if we leave Cassini orbiting Saturn for tens of years, thousands of years, whatever, it might ultimately be perturbed and fall into the moon Enceladus. They decided it was safer just to crash it into Saturn. All right? Because if Cassini had some remnants of Earth-based life on it, such as microbes that can live for years in space, and then it crash landed on Enceladus, and then later on we went to Enceladus, and we found that, hey, there's life here. Well, we couldn't be sure if we didn't bring the life there ourselves, right? So that's the reason why. So now that Cassini has ended its mission, we have nothing further planned at Saturn. In other words, there are no big missions that will go back to Saturn, possibly in our lifetime. These missions cost lots of money, more than $3 billion in Cassini's case. And they take a long time to design. They take a long time to get to Saturn. Cassini was launched in 1997, didn't arrive until 2004. And so, in other words, they take a long time to plan. If we decided we wanted to go back to Saturn tomorrow, we might not expect to be there still until 2030 or more. So therefore, in between now and any future mission we might imagine, H3+ and ground-based observations of H3+ are our primary source of continued monitoring of Saturn's upper atmosphere.